Let's talk a little bit about liquid properties. There are many applications I could talk about here, but I just want to highlight capillary action and viscosity. So if you look at paper towels or cloth towels, they're made of cotton or cellulose based from pulp. And if you dip a paper towel into water, it absorbs the liquid. If you look at this figure here, you can see how cellulose contains many OH groups and water has an OH group. So both of these can hydrogen bond with one another. And capillary action, remember, is when you have very small pores and when the water kind of travels through that material and through all the pores. And that can happen through hydrogen bonding and capillary action. Both of these molecules, cellulose and water, are polar. Now, maybe some of you have had experience with painter's tape, right? If you want to paint a line or do some trim around doors or something, you grab either masking tape or maybe some kind of cheap painter's tape that you can get from Harbor Freight or something. And this slide here shows a product called frog tape. And it's claimed to be better because the lines you get are very crisp. So when you use painter's tape, either way, whatever painter tape you use, you need to push hard onto the wall. And when you paint, okay, it's possible for some of the paint to travel under the tape through capillary action. And then when you peel the tape off, of course, before it dries, you can have jagged lines, okay? And their website and everything talk about this paint block technology. They can get nice, crisp lines. So think about it. If you're painting a latex paint, which is an oil-based paint, which is hydrocarbon-based or non-polar, and you don't want it to go under the tape, what kind of material should the tape be? It should be repellent. So your glue, for example, that holds the sticky tape to the wall could be very polar if you're using a non-polar latex-based paint. And that's basically how frog tape works. It uses a better polar glue to repel the non-polar paint solvent molecules from capillary action through it. Let me talk about viscosity. Ignore this picture here. But viscosity is resistant to flow. Syrup, for example, is a very common material that we're familiar with, and it takes a while for this to flow out. Maybe honey as well. And it says right here on the bottle, now thicker and richer. Okay, so this is mainly sugar water, high fructose corn syrup, water, and then contains 2% less of flavoring and coloring and things like that. Now, viscosity can generally result if you have high molecular weight polymers, such as poloxamer 407. So here's a mouthwash, and it's kind of thick, all right? It's not as free-flowing as water is, and they add thickeners to this so that when you pour it out, it doesn't splash as easily, okay? It also contains glycerin. Glycerin is a very polar molecule. It's a small molecule with 3 OH groups, so it's a very polar molecule that's going to thicken the solution as well. This is not the product I want to talk about, but Clorox also sells a bleach product that is sort of like a gel. It's a thick solution, so when you pour bleach into a laundry cup and you add it to your load of laundry, it doesn't splash as well. So it's convenient because you're not going to splash it onto your clothes, that you're wearing when you're doing laundry, and it won't spill out maybe when you're cleaning the house or something. Okay, so thickeners are added to different things for different purposes. Highly concentrated solutions of sugar, for example, will be very viscous. Another example is honey. And at a lower temperature, these are going to be even more viscous. You've heard of the expression, someone is as slow as molasses in the winter. In the wintertime, molasses flows very slowly if it's cooled down to low temperature. Okay. When you first pour this syrup onto your pancakes, it kind of is resistant to flow. It forms a puddle, but then when it gets heated up by your warm pancake, the solution flows even more faster, so it spreads out. Okay.